nutritional value. At a slightly higher temperature, 150 degrees Celsius, for instance, carbon compounds start to burn. In other words, the upper limit of the temperature range for carbon compounds to establish covalent bonds and maintain these in a stable manner does not exceed 100 degrees Celsius. At a temperature lower than 0 degrees Celsius, however, organic biochemistry becomes impossible, yet other compounds are different. Most inorganic substances are not affected in this way by temperature changes. In order to see this, you can place some metal, glass, or stone in a frying pan next to a piece of meat, and then heat them up. You'll see that as the temperature rises, the structure of the meat changes, it darkens, and eventually burns. Yet nothing happens to the metal, glass, or stone, not even if you raise the temperature by hundreds of degrees. Close inspection shows that the temperature needed by carbon compounds in order to build and maintain covalent bonds is exactly the range that exists on Earth. Yet, as we have already said, the temperature in the universe as a whole vary from the fierce heat of millions of degrees inside the hottest stars to absolutely zero, or minus 273 degrees. Yet the Earth created for human beings possesses just the temperature range required by carbon compounds, the building blocks of life. One more striking aspect of all this is that the temperature range is also one which water assumes a liquid form. As we saw earlier, water, one of the essential preconditions for life, needs exactly the same temperature range as carbon compounds. Yet there is no natural law that makes such a harmony necessary. This is an indication that the properties of water, carbon, and the earth were created to be compatible with one another. The flawless nature of Allah's creation is revealed in the Quran. He who created the 7 heavens in layers, you will not find any flaw in the creation of the All-Merciful. Look again. Do you see any gaps? Then look again and again. Your sight will return to you dazzled and exhausted. Covalent bonds are not the only bonds that keep the atoms in the living body together. There is a second class of bonds. These bonds of different kinds are collectively known as weak bonds. Proteins, basic building blocks, owe their complex three-dimensional shapes to weak bonds. In order to clarify this, we now need to touch on the structure of proteins. Proteins are generally referred to as amino acid chains. This is an accurate definition, though an inadequate one because the term amino acid chain calls to mind a two-dimensional series, like pearls strung out one after the other on a necklace. However, the amino acids that constitute proteins have a three-dimensional shape, like the leaves on different branches of a tree. Covalent bonds keep the atoms that comprise amino acids together. Weak bonds, on the other hand, combine amino acids together in the requisite three-dimensional form. Were it not for the weak bonds, proteins could not exist, and there could be no life in the absence of proteins. The noteworthy aspect of this is that the temperature range required by weak bonds is, as with covalent bonds, exactly the temperature range that exists on Earth. Yet weak bonds and covalent bonds have completely different structures. And there is no natural reason why they should both require the same temperature. Nonetheless, both classes of bonds are established at the same temperature. If covalent bonds were stable at a different temperature than weak bonds, then protein building would be impossible. All of this information about the extraordinary properties of the carbon atom shows that there is enormous harmony between this atom and other atoms and compounds that are the essential building blocks of life, such as water. There is also harmony between the stability of this atom to form bonds and the temperature of our planet. Our planet provides a home for all these elements and compounds. Michael Denton emphasizes this fact in his book, Nature's Destiny. Out of the enormous range of temperatures in the cosmos, there is only one tiny temperature band in which we have 1. Liquid water, 2. A great plenitude of metastable organic compounds, and 3. Weak bonds for stabilizing the 3D forms of complex molecules. As we have already seen, this narrow temperature range exists solely on Earth among all the known heavenly bodies. What is more, carbon and water, two of the main building blocks of life, are found in large amounts on the Earth. All this goes to show that the carbon atom and its extraordinary properties were specially created for life, and that the planet Earth was specially created for carbon-based life. What does a glittering diamond have in common with a drill bit? An uncut, raw diamond is the hardest of all minerals and all substances. For that reason, crystal diamond is used to cut, pierce, and plane substances of all kinds. Hardness is the resistance that minerals display to scratching due to external forces. Minerals can easily be defined according to their hardness. A mineral's relative hardness can be determined by scratching it with another. Scientists who established a scoring system in order to determine the hardness of all minerals awarded the diamond 10 points out of 10. So what is it that makes the diamond so hard? It is noteworthy that the brittle and soft graphite used in lead pencils consists of the same atoms as diamond. Like diamond, graphite is made up of carbon atoms. Yet one is very soft and the other exceptionally hard. One is like a piece of black coal, whereas the other can have a glittering surface. One is present in abundant quantities in nature, where the other is a rarity. For all these reasons, diamond is of course incomparably more valuable than graphite. So how is it that the carbon atom is able to assume both of these totally different forms? The crystal structure of the diamond is the most perfect example in the whole crystal world. The carbon atoms in a diamond crystal have the ideal geometrical form to endow the diamond with its great hardness. Although graphite also consists of carbon, its atoms are not laid out in the same way as in the diamond. This state of affairs is known to scientists as allotropy. Allotropy is the existence of different physical forms of a chemical element by its atoms being arranged in different ways. Each of these different forms is known as an allotrope. For example, Oxygen and ozone are allotropes of the oxygen atom. Diamond, graphite, and amorphous carbon are all allotropes of carbon. Some of the physical features of diamond and graphite are as follows. As we can see, there are enormous differences between these two substances, based solely upon the difference in the arrangement of their atoms. All of the properties that make the diamond valuable depend on conditions emerging during its formation. The extraordinary conditions necessary for the diamond to form are extreme heat and extreme pressure. The diamond is born in the depths of the Earth's crust. Parts of this that contain melted diamond may erupt onto the surface and freeze, although this is a very rare phenomenon. That explains why the number of diamond seams on Earth is very low, there being only a few rich deposits. The structure of natural diamond and the way it forms have served as a guide for scientists, thanks to which artificial diamonds can now be manufactured. In some experiments, graphite kept at a pressure of 100,000 atmospheres and at a temperature of 3,000 degrees Celsius was converted into diamond. However, synthetic diamonds are not as valuable as natural ones. Because of their hard structures, such artificial diamonds are used as a kind of abrasive in industry. As Sidgwick the chemist has said, the carbon atom, which contains only 6 protons, 6 neutrons, and 6 electrons, is a fully fledged miracle. The difference in the way the atoms are arranged gives birth to such different outcomes. The way that these outcomes are so beneficial for man is sufficient for us to see that all these are a blessing from Allah. Therefore, it is impossible for any of the properties of the carbon atom, which are so essential for life, to have come about by coincidence. Allah created the carbon atom with all of its different characteristics, just as He did everything else. What is in the heavens and in the earth belongs to Allah. Allah encompasses all things.